Hi, my name is Paul Mattingly, and I will be discussing the thermoplastic polymer polycaprolactone, or better known as PCL. The research study that I will be discussing today is about the polymer degradation and stability of PCL scaffolding in fused deposition modeling. So the main focus of this study is in respect to bone tissue engineering. What they're really concerned with is how to change the degradation rate of these scaffoldings in the body to better match the natural tissue regeneration of a person. So they studied the effects of filament shifting and the porosity and surface area volume. In this experiment, there was two separate types of PCL used. One was PGLA and the other was PLCL, and this was mainly to compare to see which material would be most ideal to be used in bone tissue engineering. And particles of TCP were also added in increments to see if that had any positive or negative effect on the degradation rate of the scaffolding. And there were several instruments used to measure the scaffolding for this degradation, and the main two were the scanning electron microscopy and the atomic force microscopy, which is shown in the diagram to the right. The key results from study 1 on the degradation of the scaffolding shows that the PLCL degraded faster than the PLGA, but the addition of the TCP particles had little to no effect on this degradation rate. The next part of study 1 was about how the filament shifting affected this degradation rate. In the diagrams A through C, those are the filaments that have not been shifted, and D through E show the filaments after shifting. The filament shifting of the polymer scaffolding did have an effect on the molecular weight loss. There was a slight increase for both the PLGA and the PLCL, but those two materials did have very different behaviors even without the shifting. From the plot to the right, you can see that the PLCL saw a very sharp decline in molecular weight after about 12 weeks, and at about 24 weeks, the material scaffolding was almost completely degraded. But the PLGA was a bit more consistent in its degradation, but even at 48 weeks, you can see without the filament shifting, there was still some scaffolding left. Study 2 looked at the effect of this filament shifting on the porosity and the volume, surface area to volume ratio for the scaffolding. So for the PLCL, you can see that it had much lower porosity than the PLGA, but the filament shifting didn't have an effect on this porosity. But the filament shifting for both materials did increase the surface area to volume ratio. Study 2 also looked at the effect of this filament shifting of the scaffolding on the overall permeability of the structure. The figure shown on this slide shows that the non-shifted scaffolding had a much higher permeability than the shifted, meaning that fluid flow through the architecture was much easier. Overall, this study shows that the PLCL degraded faster than the PLGA and it was less porous, but the filament shifting of the scaffolding did have an increased effect on this degradation rate and also increased the surface area to volume ratio, but it had very little effect on the porosity of the scaffolding. So the results pretty much show that this filament shifting is useful in bone tissue engineering, and it allows better matching of this degradation rate to the tissue engineering and could be very useful for bone tissue engineering in the future.